suppose you have a capacitor and you have a battery, and let's say the battery is of V0 and you are connecting this across the capacitor so that the capacitor is fully charged to the charge Q0. And if capacitance is C, we know that Q is equal to CV, so the maximum charge Q0 will be equal to CV0. This is the maximum charge stored on the capacitor, maximum charge on capacitor. Once you disconnect this capacitor, the charge will still be there, Q0, and when you connect it across the inductor, the capacitor will try to discharge through this. The moment the current begins to flow, charge on this plate decreases from Q0 to Q. We know that here Q will be less than Q0. So when Q is less than Q0, what happens? It begins to flow, the current is here. Because of the decrease in charge, the current is flowing, so the current I equal to minus dq divided by dt. So when the current begins to flow in this direction, it will develop an EMF which will be opposite to this. That means that here it will develop plus, here it will develop minus, so that it tries to oppose the current. So if we apply Kirchhoff's voltage law across the loop E, B, C, D, when you move from here to here, and its its capacitance is C, right? So the voltage across a capacitor, because Q is equal to CV and V equal to Q by C, because this is not Q0 now, so the voltage across a capacitor is Q divided by C. And because when you move from negative to positive, it is plus Q by C. When you move from positive to negative, it is minus. The EMF developed across the inductor, that we know EMF is equal to minus L into di by dt. So minus L into di by dt, which is equal to 0, since there are no batteries here. So, but we know L is minus dq by dt. Let's substitute it here. Q by C minus L into d by dt of minus di by, dq divided by dt. dq divided by dt equal to 0, which means that, and you also multiply this with L, you know that a q by LC, minus into minus plus, and L will come when you divide this whole equation by L. Here L appears, here this L is getting cancelled, so d square q divided by dt square is 0. So we have seen this equation elsewhere. This is the equation of a simple harmonic motion. If you want, I'll just write this in a familiar form. D square q divided by dt square is equal to minus 1 by LC into q. And the simple harmonic motion that we have seen is acceleration equal to minus omega square x, or in other words, acceleration is d square x by dt square, so it is minus omega square into x. Comparing these two, or let's call this omega naught as the resonant frequency of the LC oscillation circuit. So compare this equation 1 and this equation 2. You know omega naught is equal to 1 by omega naught square is 1 by LC, and omega naught is equal to 1 by root over LC. It's an important thing. L is equal to this thing, and remember this equation also. And the next thing, because we know this, force is equal to mass into acceleration. Mass into acceleration is d square x by dt square. So here the electrical displacement here is q, and the equivalent of displacement here. In such case, we write EMF is equal to L into di by dt, which can be written as here EL into d square q divided by dt square. So the coefficient of acceleration is m, the coefficient of electrical acceleration, because q we assume it as charge, electrical displacement. So d square q by dt square is equivalent of electrical acceleration, so the coefficient is L. So m is actually m refers to inertia, right? So the equivalent electrical inertia here, the equivalent of m in LC circuit equal to L. And we also know that F is equal to ma, which is m into d square x by dt square is very much equal to this forced oscillation spring. Suppose if spring is involved, we know that force is equal to kx, then which means d square x by dt square is equal to minus k by m into x. So from this relation, you know omega naught square or omega square is equal to k by m. So here omega square is equal to 1 by LC. If m is equivalent to L or L is equivalent to m, then k will be equal to 1 by c. So k will be equal to 1 by c. So m here is equal to L, k will be equivalent to 1 by c. So the equivalent force constant or spring constant of LC circuit. The other thing, at the beginning, so since this represents simple harmonic motion, the equation of the charge q is equal to either q naught sine omega t, or it will be q naught sine omega t plus or minus phi will come. But here we know the q will be maximum at t equal to 0. So t equal to 0, it should be maximum, means the equation could be q equal to q naught omega t plus pi will be 90 degree. So it is sine of omega t plus pi by 2. So the charge at any instant on the LC circuit q naught sine omega t plus pi by 2, or in other words, this can be written as q equal to q naught sine of 90 minus plus theta is cos of omega t. So this is the equation of the charge on the capacitor. Equation of charge on the capacitor. So a few things which we here compare. So F is ma, this one, and that is equivalent to this. So compare these two equations 1 and 2, and here resonant frequency is 1 by root over LC. So the electrical inertia is inductance, and the force constant is reciprocal of the capacitance, and the displacement at any instant here is electrical displacement is charge at any instant on the capacitor, and that is given by the relation q equal to q naught cos omega t. So remember, so electrical displacement is q, electrical inertia is L, and in electrical circuit the force constant equivalent is 1 by c, and q equal to the charge at any instant on the capacitor is equal to q naught cos omega t.